Hello everyone. Today we're going to see a topic which is binary tree preorder traversal. Okay, the problem says, given the root of a binary tree, return the preorder traversal of its nodes values. So we have this binary tree, which is 1, 0, 2, and 3. Okay, so a, a tip that I can give you is that binary tree preorder traversal, it starts from the root. Later we move to the left, and later we move to the right. Okay, so let's have this in mind and we go with this approach. So root 1, we add this. Later we move to the left, there is nothing. Okay, we move to the right. Okay, we have found something, we have found 2. Okay, so we add 2. We move to the left, we have 3. Okay, we move to the left. Oh, there is nothing. Oh, we move to the right. Oh, okay, there is nothing. Okay, I move to the right. Oh my God, there is nothing. Okay, we have finished. So we have 1, 2, 3, and that's over. Okay, but we're gonna see this in a better example. So I'm gonna use my code here. So remember root, left, right. Okay, so we start from the root. We have 8. We move to the left. We have 3. We move to the left. We have 1. Okay, so there's nothing. Okay, we move to the right. There's 6. We move to the left. We have 4. Okay, there's nothing. We move to the right. Okay, there's 7. Okay, there's nothing. We go back with 10 because this is the right side. Okay, so we have 10. Later, the left. Oh, there's nothing. Right again. Oh, we have 13. We move to the left. We have 13. We move to the right. Oh, there's nothing. Okay, we already finished. So the preorder for this binary tree, it's going to be 8, 3, 1, 6, 4, 7, 10, 14, and 13. But we have two approaches in order to solve this code. We have the recursive and the iterative approach. And it's really important that we know both approaches because it could be a great way to say that you know how to solve it in different ways. And actually, it shows that you have knowledge in this kind of problem. So we're going to start with the recursive one. And really, I love the recursive solution because it's really easy. It's not that hard. It's something easy to remember, and it's something that I love. So, okay, the only thing that they give us here is root. If root is none, it means that we don't have anything. What do we return? Okay, so if we don't have anything, I'm gonna give you anything. So an empty array. Else, what we're gonna return? Okay, I'm gonna return to you a root dot val, the val that I have there, plus here it's going here it's where a recursive starts. Where I was about to say recursiveness. I don't know if that word really exists or it's something that I have just invented, but okay. So here's the recursive time. So preorder traversal. Okay, but let's not forget the self dot preorder traversal, and here I'm gonna do root, and we start from the left, plus actually this is pretty same, but it's gonna be root right, and that's all. That's the recursive code. So we're gonna run our code, and it is accepted. So if we submit our code, actually it is accepted. So it's faster than 89.99% of our, sorry, 79% of the Python 3 line submission. So that was success. But now we're gonna use it in the iterative way. So for the iterative, as we saw here, we're gonna use a stack. So I don't know if you remember, but the stack approach is the first in, the last in, the first out. So it's FIFO. Okay, so first in, first out. And that's what I'll do. Okay, so what firstly we want to output is our left side, right? But if we do so, for example, we have a stack. I'm gonna put here the stack. But if we add firstly our left side and then our right side, what's going to happen? Oh, the first thing that's going to be out is the right, but we don't want that. We want that the first thing to be out, it's going to be left. Okay, so this is okay. But what we have to do, so as you see, we have to revert the order. We have to put first right and later left. So the first thing that's going to be out is going to be left. Okay, so let's start. Okay, now that we have that in mind, let's start code. Here I'm going to define a stack. Sorry, stack. And it's going to be equal. Firstly, we're going to put the root. And after I go the root, I'm going to put the result. So result it's also empty. So, okay. Again, we're going to start with the edge case. What if we don't receive nothing? So if root is none, return result. Okay, so if it is, okay, so if we don't have something that it's none, well, we're going to do it's the following step. While our stack is not empty, sorry, while our stack is not empty, okay, while our stack is not empty, what we're going to do next? Okay, so we're going to stop stack.pop. Okay, so stack is equal to stack.pop, which is our last value, and our result it's going to be equal to result, no, sorry, it's result dot append, and we're going to put the value of a stack. Okay, no, sorry, we're going to return, oh, sorry, I'm forgetting, it's okay, no, I'm just confusing out this exercise. Okay, so let me analyze the stack root result if root is known. Okay, no, this is not a stack. We're going to start with a root. So because it's root, so we're going to return is root.val. Okay, so root is stack pop, result append, root val. Okay, that's better. And you're going to see why. Okay, now what we're going to do is that we're going to add more elements to our stack. Okay, so we have seen it that first we have to start from right. If root dot right is not none, let's add stack dot append root right. Now the other case, if root dot left is not none, stack dot append root left. Okay, so we're gonna do all that, and once we finish, we're going to return our result. So I'm gonna write my code. So it is accepted. I'm gonna submit. Yeah, and it is accepted. As you can see, the recursive approach is faster than the iterative, but I'm gonna explain you here what's going on. So what's happening? What's happening here? Okay, so I'm gonna explain you the approach of this code. So here we have our stack, and also here we have our result. Okay, so we're gonna start. Firstly, we have our stack.root, which is 8. So if root is none, okay, we stop doing this case. We're going to the stack. Okay, the stack it's not empty, right? So root it's gonna be equal stack.pop. Okay, so that's my root. Result it's gonna be so stack.pop goodbye 8, and now I'm gonna go with result. result, append, root, val. So I'm gonna add here 8. Hello, also, if root dot right it's not none, okay, do dot right is not none, I'm gonna add it. So I'm gonna put here 10. Oh, sorry, 10. Okay. Later, if root dot left is not none, okay, I'm gonna add left. Okay, so left it's 3. That's okay. So our stack is not empty. Okay, so the next number it's gonna be 3. Okay, so 3. Goodbye. I'm adding 3. Okay, so if root dot right it's not done, root dot right is not done, I'm going to add stack dot 6, and later I'm going to add the root dot left. It's 1, so I'm gonna add 1. Okay, 10, 6, 1. Okay, that's better. Okay, so we'll start again. If stack it's not empty, okay, that's cool. So stack pop, goodbye 1. I'm adding here 1. Okay, so 1 is actually none, so I'm doing anything. And later 1 of left, it's none, so I'm not doing anything. So now we're going with 6. Okay, so 6, goodbye. I'm adding to the result. So result, which is root to right, it exists. So I'm gonna add 7, and later I'm gonna add left, it actually exists 4. Okay, so I'm gonna start stack, it's not empty. Root, I'm gonna take 4. So it's 4. Okay, 4 left exists and 4 right exists. No, okay, so I'm going with the other element because our stack it's not empty, and I'm gonna take the next number, which is 7. Okay, 7, I have already taken 7. So, okay, 7. And now I'm going to take, we don't have anything in left, we don't have anything in right. So we take the other element, which is 10. Our stack now is empty, but don't worry because we're going to start with the next element. So if root right, it's none. Okay, right, it's none. Okay, so we have 13. And in the left side, we don't have anything. So now we're going to take 14. So I'm going to take here 14. And actually, if root right exists, it doesn't exist, but root left exists. So I'm going to append 13. So 13. And our stack is left empty. So I'm going to take out 13. And now I have here tick, okay, our stack is empty, and I'm going to return this result. And as you can see, this result is the same that we have already seen. And for the reason our code now works. And that's everything from today. So you learn how to do the amazing pre-order traversal of a binary tree. So thank you very much. And I hope that this video has helped you. See you in the next time. Goodbye.